Unit 1, Lesson 7 brings about radicals and conjugates. Well, what's a conjugate? Well, we'll get to that in a second, but we're going to talk about radicals because Chapter 1 is all about polynomials, which just means multi-termed expressions. So we've got to see it and look at everything that can be put into a mathematical expression. So we're going to step back a little bit here and remember what we do with radicals. So remember reducing radicals? Here, we'll call this example 1. You have the square root of 50. And in order for us to work with the square root of 50, we'd like to break it down into the smallest possible numbers. So what we do is we look for the biggest perfect square that goes into 50. The square root of 25 is 5, and then we can't take the square root of 2. These are the same numerical values. If you were to put them on a calculator, you remember, you'll get the same decimal. It's much as the same if I gave you the fraction 50 over 100 and I asked you to reduce it. 5 over 10 is not reduced completely. We would take it down to 1/2. So we try to reduce radicals completely so that what's left in the radical has no perfect squares that can go into it. But radicals aren't only squares, as you can see in example number 2. This is a cube root. So we want to look for perfect cubes that go into 32. So I'm going to show you a little different way that you can break down radicals. I know I showed this to you in 8th grade, but as a quick review, you can do a factor tree. You can say the cube root of 32. Well, I can break 32 into 8 times 4, and then 4 can be broken down into 2 times 2, and then 8 can be broken down into 2, 2, and 2. And these all have cube roots over them. That's why sometimes I just do it in my head and I don't even bother to put the cube roots down because it takes too long. So now since they're cube roots, what I'm looking for are groups of 3. So what you can see here is that 8 was a perfect cube because 2 times 2 times 2, 3 2's got me 8. So if I were to reduce radical 32, really what I'm seeing is the cube root of 8 times the cube root of 4. The cube root of 8 is 2, and the cube root of 4 does not exist. So here we're looking for, in example 1, we're looking for perfect squares, which means 2 numbers that multiply together. And here we're looking for perfect cubes, which means 3 numbers that multiply together. And did you also remember that you can't have a radical in the denominator? So we did something called rationalizing. That means we want to get the radical out of the denominator. And it was pretty easy to do. Since radical 3 didn't belong here, we multiplied top and bottom by radical 3. Remember, that's really multiplying by 1, so we're not changing the worth of the fraction. We're simply getting a radical out of the denominator. 3, radical 3 goes up top, and on the bottom we have 2 times radical 3 times radical 3, and that's where the magic happens. Remember, this is square root, square root. Radical 3 times radical 3 is radical 9. Radical 9 is really 3. So it's 3 square roots of 3 over 6. Now hopefully you don't need that middle step. You realize radical 3 times radical 3 is 3. But let's look, we're not done Because just like up here when I use this, telling you that fractions always have to be reduced, this fraction has to be reduced. So who does the 6 reduce with? The 3 or the radical 3? Well, 6 can only reduce with 3 because 6 is not a radical. 6 is an integer, and it can only reduce with another integer. This is an irrational number. So an irrational number cannot reduce with a rational number, which is an integer. Reduce. Final answer is radical 3 over 2. It's not any different with this. Your mind should go, fraction, all fractions have to be reduced. Fractions can't have 0 or radicals in denominators. And we got that stinking radical 2 there. So I'm going to multiply top and bottom by radical 2 again. Hopefully on the bottom you can take the shortcut. Radical 2 times radical 2 in your mind can go as radical 4, and the square root of 4 is 2. Up top, however, you have a binomial. So it's really 3 radical 2. You have to distribute this radical 2. Now radical 2 and radical 4 can get multiplied together to get me radical 8, but looky, radical 8 can get broken down because there is a perfect square of 4 that goes into 8. So if I keep doing this, I have 3 radical 2 plus 2 radical 2 all over 2. Now here, and again, this is stuff we went over in 8th grade, here's where it gets a little dicey. Some kids want to reduce the 2 and the 2. That's wrong. This is saying everybody here is being divided by 2. Can 3 radical 2 be divided by 2? Not really. I mean, you're saying, well, I could do this, Mrs. Troll, and I could say 1.5 radical 2 plus radical 2. You're absolutely right. Now you can do it because you reduced both binomial terms here by 2. But generally, we don't put decimals with radicals. But either one is considered correct. Now you may be looking going, oh my gosh, that's a lot. Hey, this is all review. You should know it. Here's the new stuff. We run into a unique situation when we have a polynomial in the denominator that contains a radical. In this case, we have a binomial. Well, most kids think, well, this is not bad. I'm just going to do what you did here. You just multiply by one of the radicals. Okay, so if I multiply by radical 5, well, this is easy. 3 radical 5 on top. Don't write this down, it's wrong. 3 radical 5, distribute. Radical 5 times radical 5 is 5. And look, boys and girls, there's still a radical in the denominator. So this is what you're learning about today. How do you get rid of a radical in the denominator when it's in a binomial? We must use what's called the conjugate. What's the conjugate? Look how hard the conjugate is. 3 plus radical 5. But what you do to the bottom, you must do to the top to remain balanced. Did you see what a conjugate is? Yep, the conjugate is simply the same exact thing, except we inversed the sign in the middle. Why? Well, that goes back to yesterday's lesson. Remember a difference of 2 perfect squares? Watch what happens. All right, if I multiply the top across, that's not bad because it's a monomial times a binomial. So we distribute, get 9 plus 3 radical 5. Well, on the bottom, we have a binomial times a binomial. I'm going to do double distribution. First, I'll distribute a 3. 3 times 3 is 9. 3 times radical 5 is 3 radical 5. Negative radical 5 needs to be distributed now. Times 3 is negative 3 radical 5. Do you see it? And then radical 5 times radical 5 is 5. And look at the happiness that occurs in the denominator. 3 radical 5 and minus 3 radical 5 cancel out, leaving me with 9 minus 5, which is 4, a rationalized denominator. I check. I have to see, can 9 and 3 radical 5 be divided by 4? It doesn't go in and make pretty numbers, so we'll leave our answer as such. Or you can break your fraction apart so that we see the real part of the fraction and the irrational part of the fraction. And once again, either answer is correct. All right, what example are we on? I've kind of lost track here. 1, 2, this should have been 3. This was 4, 5. Okay, so now here in example 6, what we want you to realize is just the same thing. It is a fraction. Fraction can't have a 0 or a radical in the denominator. Okay, I've got 2 radicals here. So I'm going to multiply by its conjugate because it's a binomial. Top, getting pretty easy. Binomial, multiply by monomial. 4 radical 10 plus 4 radical 2. On the bottom, binomial times binomial means double distribution. First, I'll pass out a radical 10. Radical 10 times radical 10 is 10. Radical 10 times 2 is radical 20. Negative radical 2 has to be distributed now, so it gets me negative radical 20. And radical 2 times radical 2 is 2. And that prettiness happens again. The 20s cancel out in the radical. 10 minus 2 is 8. And I have 4 radical 10 plus 4 radical 2. Now I'm going to check. Can this numerator, both of these numbers, get divided by 8? Yes. If I break it apart, I realize that the 4 and the 8 cancel down to a 2. 4 and the 8 can cancel down to a 2. So I have radical 10 over 2 plus radical 2 over 2. I can leave that as my answer, or I can combine them into one fraction. Notice the 2 cannot go into the 10 or this 2 because the denominator 2 is a real number, a rational number. Sorry, I should say it's a rational number. And radical 10 and radical 2 are irrationals. Rationals don't hang out with irrational people. And the last example, I know it's getting a little messy in here. Extend the page, bring this down so it kind of sticks out. You're looking at this and it's like square root of an entire fraction. Well, don't panic. Since the radical is over the entire fraction, it's basically asking you, take the square root of the numerator, take the square root of the denominator. Hopefully you look at this and say, well, this isn't hard. I can take the square root of 16, it's 4. Can't take the square root of 3, so it stays. And yep, we're right back to this lesson. I I can't have radicals or zeros in the denominator, so I will rationalize by multiplying top and bottom by radical 3. The numerator becomes 4 radical 3, and the denominator becomes 3. It cannot get reduced anymore. 4, the rational number divided by 3, can't happen, and we can't divide an irrational with a rational. So that's our final answer. So the summary. We're not allowed to have radicals in the denominator. We use conjugates to tackle this problem. A conjugate is a binomial that has had its second term sign inversed. We multiply numerator and denominator by this conjugate to rationalize the denominator. And I'm going to add one thing here. That's if the denominator is a binomial. I should have really put that in here. And we use conjugates to take care of binomials, right? Because if you had a monomial, then it was simple. All right, see you tomorrow.